In our mathematics class today, we shall be discussing the application of differentiation. Differentiation has a wide range of application. For example, we will discuss the application of differentiation in gradient or slope of a function at a given point. We also discuss the turning point, which is the maximum and the minimum point in a given curve. It also involves velocity and acceleration. Speed is also there. And of course, we will talk about other areas where differentiation will be applied. We now look at gradient or slope at a given point. Gradient or slope are synonymous. When you talk about gradient, you are also talking about slope. In differentiation, gradient is represented by dy all over dx, or by tan theta, where our theta is the angle of inclination with the horizontal. We are looking at a situation like this, and then you have, and we can talk about the gradient of the line AB, and that is meaning we're talking about tan theta, which is the angle of inclination with the horizontal. We are now going to take some examples so that you can clearly see how to calculate the gradient or a slope of a curve at a given point. I want us to also note that the gradient of a straight line is always the same at any point on the straight line. Whereas, in the case of a curve, the gradient is not the same at any point. Assuming this is your curve, and then this is a curve AB, and you are looking for the gradient at this point. The gradient at this point will give you drawing a straight line that we pass through that point like this. We have a straight line passing this point. We can find the gradient at this point. In a similar way, if you are looking for the gradient at a point here, it means you are going to draw a tangent to that point in this way. Alright, you will realize that if we are to find the angles at the horizontal, assuming you have this case, this angle here is theta 1, whereas this angle here is theta 2. And you know that the angle here and the angle here, they are not equal. Hence, we are saying that the gradient at any point on a curve is not the same all over the curve. So the gradient at this point, P, is equal to tan theta 1, while the gradient at this point, Q, is equal to tan theta 2, and they are different. We shall now take an example. We take the first example, number 1. Find the slope of the curve y equal to 2x squared plus 5x minus 3 at the point s equal to 1 and y equal to 4. Recognize the word slope, and we said that slope also means gradient. And then also identify that it is the gradient or slope at a given point where s equal to 1 and y is equal to 4. So our solution, we have our y equal to 2x squared plus 5x minus 3. Now, slope means the y all over the s. And then if you differentiate this component by component, we have 4s, and then if you differentiate 5s, you have 5. Of course, if you differentiate minus 3, it is 0. Now, we are going to evaluate this at s equal to 1, there is no point considering y equal to 4 because the derivative does not have a y variable. So when you consider the derivative at the point s equal to 1, you will now have our dy all over ds to be equal to 4 times 1 plus 5. And the result is equal to 4 plus 5, and that will give you 9. So that gives you the gradient of that function y at the point where s equal to 1 and of course y is equal to 4. Example number 2. If the gradient of the curve y equal to 2ks squared plus s plus 1 at s equal to 1 is 9, find k. Okay, solution. Observe here that you are given the gradient and you are also given a function, and there is a variable, a constant there, k, you are asked to find. The process remains the same. You have y equal to 2ks squared plus s plus 1. We will now differentiate this with respect to s, and that's 2 times 2 is 4 times ks, because if you subtract 1 from 2 is 1, so s to the power 1 is s, and then plus, if you differentiate s, you have 1, and of course the constant 1, the derivative is 0. Now, if you now evaluate this at s equal to 1, we have that our dy over ds will now be equal to 4k times 1 plus 1. The result is equal to 4k plus 1. And that this derivative, the gradient, is equal to 9. So therefore, our 4k plus 1 is equal to 9. Solving for k, we have that 4k is equal to 9 minus 1, taking or collecting like terms. And of course, when plus 1 crosses over the equation line, it becomes minus 1. And of course, using the balance method, it means that subtract 1 from both sides, and you now have 4k equal to 9 minus 1, which will be equal to a. So finding k, divide both sides by 4 to give you 8 all over 4, and the value is equal to 2. So you will have find the value of k using this process. Example number 3. The expression as squared plus bs plus c equals 5 at s equal to 1. If the derivative is 2s plus 1, what are the values of a, b, and c respectively? Solution. We have the expression, let's say y equal to as squared plus bs plus c. At s equal to 1, we have a into 1 squared plus b into 1 plus c. And this will give us a plus b plus c. And that this is equal to 5. This is our first equation. It went further to say that if the derivative is 2s plus 1, so what is the derivative of the function? So let's find dy over ds. Our dy all over ds will be equal to 2as plus b. And that this derivative is equal to, that is 2as plus b is equal to 2s plus 1. Okay, if that is the case, at s equal to 1 again, you will have, at s equal to 1, you have 2a plus b is equal to 2 plus 1, resulting in 2a plus b is equal to 3. This is our second equation. From 2, we have that our 2a is equal to 3 minus b, or our b is equal to 3 minus 2a. Now, we know that the sum of a plus b plus c must be equal to 5. So we can try the value of a. So if a is equal to 1, then we have b will be equal to 3 minus 2, and that is equal to 1. And so if a is equal to 1, our b is also equal to 1. Therefore, our c will be equal to 5 minus 2, because 1 plus 1 is 2, and that will be equal to 3. So the values of a, b, and c required of us are a equal to 1, b equal to 1, and c equal to 3. Let us now consider the turning points. By this we are talking about the maximum and minimum points or values. For a quadratic function, say y equal to ax squared, we have the u or the n-shaped graph. If we draw the quadratic graph, we are going to have this U-shape or the N-shape. This parabola here, each of them has a turning point. Look at the turning point here. Look at the turning point here. It comes down, from here it rises. It rises, from here it falls, like a projector. At the turning point, at this point where you have the straight line making a tangent to the curve, at those points, that is this point here and this point here, dy over ds is equal to 0. It means that the gradient is equal to 0. And of course, looking at the straight line, is neither rising nor falling. It is horizontal. And that is why the dy over ds, which is the tangent, is equal to 0. Now, the point can be minimum or maximum. From the two cases we have above of the two graphs, the parabolas, you have that at each point here, it can be a minimum point, and here is a maximum point. Minimum means at the point where the graph is lowest. Maximum at the point where the graph is highest. And this eventually will lead to a minimum or maximum value as well. That is to say, when you have determined the minimum point, you can now substitute the minimum point in the original given function to get the minimum value. So also, when you have the maximum point, you substitute it in the given function to have the maximum value. But for the cubic function, such as y equal to ax cubed, a can be negative or positive. If this is positive, then you will have a curve, a cubic curve. If a is negative, you have also the same cubic curve, but the starting point differs. In this case, it rises, falls, and rises. And so we have at this point here, and then we also have at this point here, two turning points in each of the cases. In this case, you have a turning point here, you have a turning point here, which also translates to say that you have a maximum point here and a minimum point here. So also you have a maximum value and a minimum value. Similarly, you have this case. falling, rising, and falling. You have here the minimal point and minimal value, and here the maximal point and the maximal value. At each of these turning points, your dy over dx is always equal to 0. Let us now look at the determination of a minimal and a maximal points. We say that for a minimal point, the necessary and sufficient conditions for the existence of a minimal point are 1. dy all over dx must be equal to 0. In other words, you will differentiate the given function and equate the derivative equal to 0. 2. Your dy over dx changes sign from negative to positive, falling to rising. It's falling, it's rising, it's falling, it's rising. So you must be able to determine that, for it to be a minimum point, it must fall and rise. So this is a minimum point. But it rises and falls. This cannot be a minimum point. But it falls and rises. This again is a minimum point. The third case is when the second derivative of the given function is greater than 0. In this case, at that point, you have a minimum point. Similarly, for a maximum point, you have condition 1 remain the same, dy over dx equal to 0. Condition 2, dy over dx changes sign this time around from positive to negative, rising and falling, rising and then it falls from positive to negative. You will now have a maximum point. Again, the second derivative of that function will be less than 0. Evaluated at the given point will be less than 0. So when you find the second derivative and then you evaluate it at the given point and it is less than 0, then you have a minimum point at that point. There is a situation where they find a curve neither rising or falling at a point. For example, you have a curve, or it is coming like this. You will realize in this case that it is not rising or falling at any point on the curve. Rather, it flexies. It flexes or flexes at a point, at a particular point. It just flexes, you know. So it's neither maximum or minimum. So we refer to that maybe at this point as a point of inflexion, a point where it flexes, like here now, a point where it flexes. Just go flexing. So it is neither maximum nor minimum. In this case, we say that neither minimum nor maximum. Neither minimum nor maximum, as far as this case is concerned. And such a situation is what we refer to as the point of inflexion. How do we recognize this? We have the necessary and sufficient condition. Necessary and sufficient condition will be for the existence of inflexion are 1. dy over dx is equal to 0. 2. The second derivative is also equal to 0. And 3. The third derivative is not equal to 0. These are the necessary and sufficient conditions for the existence of inflexion. Necessary and sufficient conditions for the existence of inflexion. increasing and decreasing functions. Number one, if y decreases as s increases, y decreases as s increases, then dy over ds, which is the derivative of that function, will be less than 0. Anything less than 0 is considered as negative. Take example of this curve. If you look at this curve, the value of y of s as is increasing, the value of y decreases. Take a look at it like this, and then you have this, the s and the y axis. Now let's say we have some points here, and so if this is 1, we will now have corresponding value of y. If this is 2, we now have corresponding value of y. If this is 3, you have corresponding value of y. If you look at this 1, maybe this point here is 3, this point here is 4, this point here is 5, assuming you realize that as s is increasing, when s is 1, y is 5. When s is 2, is increasing, but y now is 4, is decreasing. This condition, our dy all over ds is less than 0. Secondly, if y increases as s increases, then dy over ds must be greater than 0. That is positive. Take a look at this. From what you have in this case, let's assume that this is our graph, and it goes like this. This is our origin. This is your y-axis. This is your s-axis. If you take a value anywhere here, let's take some values and see what happens. Maybe when s is 1, the value of y is here. When it is 2, the value of y is there. When it is this point, the value of y is here. When it is here, the value of y is here. So you discover that it is rising. As s is increasing, y is also what? Increasing. Or as y is increasing, s is also what? Increasing. In such a case like this, the derivative must be greater than 0. That is positive. In conclusion, therefore, the derivative of a function is positive over the range where it is increasing, and negative where it is decreasing. We also need to mention another very important concept, which is stationary point. Stationary point. By the word stationary, it means a kind of a standstill point, a point where it is not moving. When you throw a stone up, it gets to a point where it no longer moves. It does not project further. Rather, from that point where it does not project further, it begins to come down. That point is a stationary point. It is neither rising nor falling. So, a point on a curve at which the derivative, that's dy over ds is equal to 0, is called a stationary point. Remember, at that point, the tangent is equal to 0 because it's a straight line. And the value of the function at that point is called its stationary value. In other words, you get the stationary point, you substitute it in the given function to give you the stationary value. At such points, the tangent is parallel to the s-axis. The tangent is parallel to the s-axis. We have explained that before. So we solve the equation dy all over ds equal to 0 to find the stationary points, from where we substitute the stationary point in the given function to get the stationary value. Let's take the first example, number 1. determine the maximum value of 3s squared minus s cubed. Take note, we are to determine the maximum value of this. Recognize this, that this is a cubic function because the highest power of s is 3. And that's why we say the degree of s here is equal to 3. The first thing we do, remember, is that for maximum or minimum, dy over ds must be equal to 0. So, in our solution, we have let y be equal to 3s squared minus s cubed. Then we find our dy all over ds, which is equal to 6s minus 3s squared. Good. So now that we have found our dy over ds to be equal to this, therefore, we have that our 6s minus 3s squared must be equal to 0. Factorizing this, you have 3s into 2 minus s is equal to 0. This will give you 6s, this will give you minus 3s squared. So that your 3s is equal to 0, or your 2 minus s is equal to 0. Here, your s equal to 0, or your s is equal to 2. So we have 2 points. The point where s is equal to 0, and the point where s is equal to 2. Which of them is a maximum point? Which of them is a minimum point? To determine which of them is a maximum or minimum point, we take the second derivative of the given function. So ds squared, d squared y over ds squared will be differentiating this. When you differentiate this now, you will have differentiate 6s to give you 6, and differentiate minus 3s squared to give you 6s. Now you are going to evaluate this one at the point where s is equal to 0. So at s equal to 0, we have that 6 minus 6 times 0, and that is equal to 6 minus 0 is 6, and this is greater than what? 0. Therefore, we have a minimum point at s equal to 0. We do the same thing at s equal to 2. We have 6 minus 6 times 2, which is 12, and 6 minus 12 is equal to minus 6. This is less than 0. Therefore, you have a maximum point at s equal to 2. So the question is, determine the maximum value of this. We will now substitute the value of s equal to 2 in the given function to get the maximum value. So, substitute your s equal to 2 in the function which is 3s squared minus s cubed. And of course that will be 3 into 2 all squared minus 2 raised to the power 3. 4 times 3 is 12, and 2 raised to the power 3 is 8, and giving you the value 4. So this is the maximum value of the function. Therefore, the maximum value is equal to 4. We want to also quickly note that similarly, take note that if we were to find the minimum value, similarly for a minimum value, if we are to find the minimum value, we'll substitute s equal to 0. We substitute s equal to 0 in the function given to us, which is 3s squared minus s cubed. And that will be equal to 3 into 0 squared minus 0 cubed, and of course everything here is equal to 0. That becomes the minimum value. So the minimum point is s equal to 0, and the minimum value is equal to 0. Example number 2. Here we are given that the maximum value of y equal to 1 plus hs minus 3s squared is 13. We have to find the value of h. Take note, the maximum value has been given to you as 13. Before we arrive there, what is the process? This is the process. Solution. We have y equal to 1 plus hs minus 3s squared. Remember, to find the maximum value, you need to find the maximum point. To find the maximum point, you need to differentiate the function. That is to say, by finding dy all over ds. And this is equal to h minus 6s. And of course, for you to get the maximum point, therefore, our h minus 6s must be equal to 0. In other words, as far as this case is concerned, we have that our h is equal to 6s. And so, our s will be equal to h all over 6. Now, this gives you the value of s. And because they're talking about the maximum value or so, and we have only one value of s, which is h all over 6, we then first take it that this is a maximum point. And this will now give you a maximum value. Therefore, the maximum value, given that s is equal to h all over 6, will be equal to 1 plus h times h all over 6 minus 3 into h all over 6 all squared. If you now simplify this, you will have 1 plus h squared all over 6 minus 3 h squared all over 36, which eventually will give you 1 plus h squared all over 6 minus h squared all over 12. And we are told that the maximum value is equal to 13. So we equate all this to 13. So solving this, you have 12, that is clearly the fraction by multiplying all through by the LCD, which is 12. So we have 12 times 1 is 12. And 12 times this will give you 6, we cancel 12, 2 times h squared will give you 2h squared. And then 12 into 12 is 1 times h squared is h squared. Everything is equal to 13 times 12. Alright. Having this, we now have that our 2h squared minus h squared will give you h squared. And this will be equal to your 13 times 12, which is 6. And that is 12 plus 3 is 15. And then minus 12. And that will give you 144. Therefore, the h, which is what you are asked to find, will be 144 under the square root. And the value is equal to 12. And that is the value of h as far as this problem is concerned. Example number 3. Find the range of values of s for which the function 1 plus 3s minus 2s squared is increasing. Increasing. The range. Solution. When the function is increasing, it means that dy over ds must be greater than 0. And our y here is equal to 1 plus 3s minus 2s squared. So find your dy with respect to s will be equal to 3 minus 4s. And this must be greater than 0. In other words, 3 is greater than 4s. And so, 3 all over 4 is greater than s, dividing both sides by 4. Therefore, your s must be less than 3 all over 4. And that is the range of values. Number 4. Find the stationary points of the function s plus 4 all over s, comma, where s is not equal to 0. Solution. Stationary point. We know that for stationary points, our dy all over ds is equal to 0. Now we have y equal to s plus 4 over s. Our dy over ds will be equal to differentiate s in 1, and then differentiate this, you will have minus 4 s raised to the power minus 2. The reason for this is because this one can be written as s plus 4 into s raised to the power minus 1. Remember the laws of indices. So that we now have this to be equal to 1 minus 4 all over s squared. And then you have to find this equal to 0. So we are solving this equal to 0. So we have 1 is equal to 4 all over s squared. Cross multiply, s squared is equal to 4, and therefore s is equal to the square root of 4, which is plus or minus 2. Which is plus or minus 2. So for the stationary points, our s is equal to minus 2, or s is equal to plus 2. Example number 5. Find the greatest value of s squared y if s plus 2y equal to 6. I want you to observe this very carefully. Our solution. Let's take the first equation there. S plus 2y equal to 6, which is a linear equation. And then here we have that our y, our 2y is equal to 6 minus s. So that our y is equal to 6 minus s divided by 2. I will now replace y by 6 minus s all over 2. So we now have, therefore, our s squared y to be equal to s squared multiplying 6 minus s all over 2. And then we have this to be equal to, if you expand this, you will have this to be equal to 3 s squared, and then we have minus half s cubed, as the case is. Now, let's take our h to be equal to this 3s squared minus half s cubed. We don't want to say y equal to this again, because we're looking for the greatest value. Let's say the greatest value is h, or is h. H is equal to this. To find the greatest value, we first of all find the greatest point. Greatest here is also synonymous to the maximum value. So we have our dh all over ds will be equal to 6s, and then minus 3 all over 2, and then we have s squared. This is now supposed to be the dh all over ds of the function a, equal to 3s squared minus half s cubed. Now remember, we are looking for the greatest value. So we need to get, first of all, the greatest point. So we equate this to 0. 6s all minus 2, 3 all over 2s squared will be equated to what? To 0. Then of course, if we do this, our s is common. We have 6 minus 3 all over 2s is equal to 0. So that our s will be equal to 0, or we have 6 minus 3 all over 2s equal to 0. In this way here, when you solve this one, you will have your 6 to be equal to 3 all over 2 of s. Therefore, we have here that our 12 is equal to 3s, and our s now will be equal to 12 all over 3, and the value is equal to 4. So our s is equal to 0, or our s is equal to 4. Which of them is the greatest point? The greatest point here is s equal to 4. Therefore, we have our greatest value. The greatest value will be to substitute the value of s in s equal to 4 in the given expression. So the greatest value is equal to, and the given expression which we factorize was 3s squared minus half s cubed, which is equal to 3. Our s is 4 all squared minus half. Our s is 4 all cubed. This is 16 times 3 is 48. And this is 4 times 4 raised to the power 3 is 64, times half is 32. And the result of this is this, and that is 1. So we have finally the greatest value of x squared y is equal to 15. Example number 6. If 60 meters of fencing are available, what are the dimensions of a rectangular enclosure with the greatest area that can be made, and what is this area? Solution. We're talking about a rectangle. Let's sketch a rectangle. Assuming this is our rectangle, let the length be s. So this side will also be s. And it therefore means that the breadth of this rectangle, since the fencing is 60 meters, that is the perimeter. So we have s plus s is 2s, then the breadth will be equal to 60 minus 2s divided by 2. So which eventually will give you 30 minus s for the breadth. If you add this together, you will have the 60 meters. So now that we have this, we are told in this case that the area A is length times breadth, which is s multiplying 30 minus s. In this regard, we have our A to be equal to 30s minus s squared. Now, because we are looking for the greatest area that can be made, we can now differentiate the area with respect to s and to have 30 minus 2s. In order for us to determine the greatest area, we now equate 30 minus 2s to be equal to 0, giving you s to be equal to 15. So we have that the length is equal to 15, and then the breadth is equal to 30 minus s, which is 30 minus 15, and this is also equal to 15, giving you a special rectangle which is a square. The area, therefore, the area will be equal to 15 times 15, and that is 225 meters squared.